Okay, so let's start out with the exercises in section 8.2. I'm going to do 2A. So in this case, you're asked to write the composition of two permutations in Tableau form. Right? So we can write this way. Let me do it this way. I'll do it a couple ways. But one way to think about this is sigma composed, mu composed sigma means you take sigma first and then mu. Now if I want to write sigma this way, A goes to C, B goes to D, then let's see, C goes to A, and D goes to B. All right. So these arrows, this B goes like that. These arrows represent sigma. All right? But then we have mu. Mu takes A to D. All right. So in fact, I can write that this way, A to D. Mu takes B to C. Mu takes C to B, and mu takes D to A. All right. So all I need to do is chase the arrows. All right. A goes to C, goes to B. Then B goes to D, goes to A. Then C goes to A, goes to D. Then D goes to B, goes to C. So this is going to be mu composed sigma. All right. Or I can write this in Tableau form as A, B, C, D. A goes to B, B goes to A, C goes to D, D goes to C. All right. Now, once you get better at this, you don't need to draw these arrow diagrams. You can just read it off the tableaus. For instance, you can just see that mu composed sigma means sigma first. A goes to C, goes to B. B goes to D, goes to A. C goes to A, goes to D. D goes to B, goes to C. All right, so you can do it in that shorter way. All right. All right, now let's take a look at exercise 8.2.5. Here we have two different sets. Both sets have two elements. Here we want to write the Cayley tables for SW and SZ. Okay. SW is the permutations on W, SZ is the permutations on Z. Now how many permutations are there on SW? Well, if you think about it, you certainly have the identity permutation, which I can write as, let me just write it as ID, that's fine. And then there's another permutation where GH goes to HG. And if you think about it, that's really the only two possibilities for SW. SZ similarly is ID. The other permutation is JK goes to KJ. Those are the only two possible permutations that you can have on the set Z. All right, so let's write a Cayley table for SW. SW means I do composition on these permutations. So the Cayley table is going to have 2 rows, 2 columns, ID, GH, HG here, and then here I have ID, GH, HG, and here's my table. And you can just fill this in. All right. So this is Cayley for SW, and then you have Cayley for SZ. Okay, and this is also going to have 2 by 2 here. Here I have ID, JK, KJ, and then here I have ID, JK, KJ. And here we have ID to ID gives R decomposed with ID. You can figure this out. It's not too hard to do these. This is going to be GH, and it turns out that GH composed, this permutation composed with itself is just the ID again. And here I have ID. It's a similar result here. And then ID here. All right, so those are my two tableaus. Okay, then let's take a look at part B. Part B says give a bijection from W to Z, that is a one-to-one onto map from this set to this set, and a corresponding bijection from SW to SZ that would show SW is isomorphic to SZ. Now, the chapter talks a little bit about isomorphism. All right, so isomorphism just means basically that the Cayley tables match up. So we want to show that we can make a map between Z and W that makes the Cayley table of one go into the Cayley table of the other one. All right, so let's give it a start. First of all, we want a bijection from W to Z. All right, now a bijection is a one-to-one onto map. So this is part B. So let's give a bijection from, and my Z was GH, and my Z was JK. Okay. Now, we can define bijection as a function. Function can be defined as a set of ordered pairs. So we can say F as a set of ordered pairs. Well, I can map G to J. That's a natural mapping. If I map G to J, then I better map H to K. All right. So here my F maps. Let's see. It was W to Z, right? So this was W, and this is Z. So F maps W to Z. Every element of W goes to an element of Z. G goes to J, H goes to K. All right. Now, I want a corresponding map from SW to SZ. All right. So, in other words, this map from W to Z produces a map from SW to SZ. So how does that work? Well, let's look at the elements of SW. SW, first you have the identity, which I could write this way, GH to GH. And then you have the other one that's not the identity, that maps GH to HG. It exchanges the two elements. Okay. Now I'm going to use F to replace G. Well, G goes to J, right? And F says H goes to K. Okay. So the result is I can say F of GH is equal to, well, the G goes to J, and the H goes to K, and this G goes to J, and the H goes to K. And that's just the identity on the set Z. On the other hand, F of GH HG is equal to, I'm going to use G goes to J and H goes to K. So here I have H goes to K, G goes to J. Okay, and that's the other one. Okay, so the mapping that I have from SZ to SW, I can also write as a set of ordered pairs. It's equal to, first of all, it takes the ID of W, to the ID of Z. And it also takes this map HG. It takes this map to this map JKKJ. All right, so here I have my function specified as a set of ordered pairs, and now it's a function on the permutations, not on the elements. All right, so that's an example of a function as asked here, and that function is a bijection, and that bijection from W to Z produces a bijection from SW to SZ. And here the SW is isomorphic to SC because this Cayley table, if I replace the G with J and the H with K, I just end up with this Cayley table. All right, now, what about part C? Is this the only bijection from W to Z that gives this isomorphism? And the answer is, actually it's not. This one, I took G to J and H to K, but I could also take another bijection from W to Z, and let me call that G. Now, as I said, I took G to J and H to K. I could take G to K, and if I took G to K, I'd have to take H to J. All right. Now, what does G do to SW? Okay. Well, remember SW has two elements. It has the identity, and it also has the other one, which is GHHG. Let's see what happens. Let's take G of the identity, and the identity I can write as GH. Now, what does G do to G? G replaces G, little g replaces big G with K. It replaces big H with J. Same here. Replaces big G with K, and replace big H with J. So that's also equal to the identity on Z. Okay. So even though F and G are different mappings on W, they produce the same result on the identity permutation. Right? So let's see what G does to the other permutation. Little g acting on GHHG, acting on this permutation. Well, I'm going to replace the G with a K, and replace the H with a J, and here on the second row I replace the H with a J and a G with a K. Okay, so that's the second permutation in SZ. And in fact, this permutation here is exactly the same as the permutation up here. So when you take the corresponding map of the sets of permutations, F and G give you the very same result. And they give you the same isomorphism between SZ and SW. So the point here is that a function defined on a set that takes one set to another set also takes the permutations on the first set to the permutations on the second set. And the function can be thought of as a relabeling. I mean, really, you can think of this permutation, G goes to H, H goes to G, as the same permutation of J goes to K, K goes to J. You're just using different letters. And that different lettering is expressed by a function from the set GH to the set JK. Okay, the last exercise I'm going to do in section 8.2 is part A of this one, and we're creating a Cayley table, and the Cayley table involves sigma, tau, and mu. Now we also have the identity, so a Cayley table will have all of the permutations involved on the rows and columns. So for part A here, my Cayley table is going to look something like this. Now it doesn't really matter what order you put the sigma, tau, and mu in. We might as well put it in the order that is given. All right. And then let's go ahead and do it. Well, we certainly know that ID composed ID is ID, ID composed sigma is sigma, ID composed tau is tau, ID composed mu is mu. ID composed anything is the same thing. Furthermore, sigma composed ID is sigma, tau composed ID is tau, mu composed ID is mu. Right, so we already got quite a bit of our table. We've got 9 entries left. All right, let's consider what is sigma composed sigma. And I hope that you can start doing this without doing a lot of rewriting. Sigma takes 1 to 1. So if I take sigma composed sigma, sigma will take 1 to 1, and another second sigma will take that 1 again to 1. Sigma takes 2 to 2, and a second sigma will take that to 2 again. Sigma takes 3 to 3, and the second sigma will take that to 3 again. Sigma takes 4 to 5. And then a second sigma will take that 5 back to 4. Sigma takes 5 to 4, and then a second sigma will take the 4 back to 5. So that's the ID. So here we have ID here. All right. Then let's think about sigma composed tau. Now remember, you have to do tau first and then sigma. Tau takes 1 to 3, and then sigma takes that 3 to a 3. So sigma tau is going to be 1, 3. Sigma tau acting on 1 gives me 3. Tau on 2 gives me a 2, and sigma gives me a 2, so that's going to give me a 2. Tau on 3 gives me a 1, and that 1 gives me a 1, so I have 3, 1 here. Tau on 4 gives me a 4, and the sigma gives me a 5. Tau on 5 gives me a 5, and sigma gives me on 5 gives me a 4. All right, now, if you take a look at this and you compare this with mu, in fact, sigma tau is equal to mu. So I can put a mu here. All right. So you just need to go through and fill in this entire table. All right, so just keep on following the same process.